Hello. Today I want to talk about part 10 of my series on essential theorems for harmonic astrology. So let me share my screen and we can get started. As usual, this will just take a minute. I'll have to get rid of some panels so I can see what I'm doing. So I'm almost there. Okay, here we are. Essential theorems for harmonic astrology, part 10, fixed points. Now, when we noted that all higher harmonics of 0 degrees remain at 0 degrees, we were essentially identifying a quantity that remains fixed in higher harmonics. And such fixed points are often of interest in mathematics. And following is another theorem that identifies points that will remain fixed in certain higher harmonics. Okay, Theorem 12. If theta is an angle with 0 degrees less than theta less than 360 degrees, and if n is a natural number, then theta is an inharmonic angle if and only if n plus 1 times theta modulo 360 degrees is equal to theta. In other words, theta is an inharmonic angle for some natural number n if and only if theta is a fixed point in the transition to an n plus 1 harmonic chart. Well, let's look at the proof, and remember, since this is if and only if, we have to prove it in both directions. Assume this, prove this, and then assume this, and prove this. So, first part, if theta is an inharmonic angle, that means that theta is equal to k times 360 degrees over n, modulo 360 degrees, where k is a natural number. Thus, using lemma 1 again, n plus 1 times theta, whole thing modulo 360 degrees, is going to be equal to n plus 1 times parentheses k times 360 degrees over n modulo 360 degrees, and then that whole thing modulo 360 degrees. Okay. And by lemma 1, this is just equal to n plus 1 times k times 360 degrees over n modulo 360 degrees. Lemma 1 says that if I'm multiplying by a natural number, and if this is a rational number, then I can just multiply them together, do the modulo 360 degrees part just once. Well, if I multiply through, distribute this product across the sum, I get k times 360 degrees plus k times 360 degrees over n. Now, what happened here is when I multiplied n by this thing, the n's canceled out, so I was just left with k times 360 degrees. Okay, now, since this is a natural number multiple of 360 degrees, this part modulo 360 is just going to be 0 degrees. So this part contributes nothing to the final outcome. So this is going to be equal to just k times 360 degrees over n modulo 360 degrees. And that is what theta is going to be. So that proves the first part. If theta is an inharmonic angle, then it's going to be fixed in the n plus 1 harmonic. We take n plus 1 times theta, modulo 360 degrees, we get theta back. Now let's go in the other direction. This is going to be a little bit longer. So if theta with 0 degrees less than theta less than 360 degrees is a fixed point in the transition to the n plus 1 harmonic, if theta's a inharmonic angle, for instance, we want less than 360 degrees. We don't need to have it equal to 0 degrees. We know what happens at 0 degrees. It just stays fixed. So we'll assume that it's strictly greater than 0 degrees and strictly less then 360 degrees. And if it's a fixed point in the transition to the n+1 harmonic, then n+1 times theta modulo 360 degrees is just equal to theta. But distribute this product across the sum, and that tells us that n theta plus theta, whole thing modulo 360 degrees, is equal to theta. Now, since theta itself is strictly between 0 degrees and 360 degrees, the remainder when theta is divided by 360 is just theta, right? It doesn't go in there even once, 0 times plus remainder. And that implies that the remainder when n times theta is divided by 360 is 0 degrees. Since otherwise, if we write n times theta as w times 360 degrees plus theta prime, where w is a whole number and theta prime is in strictly between 0 degrees and 360 degrees, then n+1 times theta modulo 360 degrees, that's equal to n theta plus theta modulo 360 degrees. Replace n theta by w times 360 degrees plus theta prime, and then we have plus this theta. Take all of that, modulo 360 degrees. Well, again, a whole number times 360 degrees, that is contributing nothing when we do this modulo 360 degrees. So this just reduces to theta prime plus theta modulo 360 degrees, which I claim is not equal to theta. Okay. Now, to see this more clearly, notice that if theta prime plus theta, if that comes out equal to something less than 360 degrees, then theta prime plus theta modulo 360 degrees is just equal to theta prime plus theta, but that has to be strictly greater than theta since theta prime is not equal to 0. On the other hand, if theta prime plus theta is greater than 360 degrees, then theta prime plus theta modulo 360 degrees, I claim that will be less than theta since less than 360 degrees has been added to theta. So what you're adding on to theta is less than a full circle, less than 360 degrees. It's going to be, by assumption, greater than 360 degrees, but where you end, that's going to fall short of where theta is. So this whole thing, modulo 360, comes out less than theta. On the other hand, if theta prime plus theta is equal to 360 degrees, then n+1 times theta modulo 360 degrees, again, that's equal to n theta plus theta modulo 360 degrees. You can rewrite n theta as w times 360 degrees plus theta prime. And then you also have your theta to add on. And when you do this modulo 360 degrees, well, if theta prime plus theta is 360, then this comes out to w times 360 degrees plus 360 degrees. That's modulo 360 degrees. You can factor out the 360 degrees, right? That is w plus 1 in brackets times 360 degrees. This is a whole number times 360 degrees, so modulo 360 degrees. That is going to be equal to 0 degrees, which is not theta, since we assume that theta is strictly greater than 0 degrees and strictly less than 360 degrees. And that contradicts our hypothesis that n+1 times theta modulo 360 degrees is equal to theta. So this means that our assumption that this remainder theta prime is strictly between 0 degrees and 360 degrees is incorrect. Now, whatever remainder we get, it has to be less than 360 degrees because we were dividing by 360 degrees. We divided that into n theta to get this expression up here. So the part which is causing the problem is this assumption that theta prime is greater than 0 degrees. So to fix that, it must be the case that theta prime actually is 0 degrees. And from that, it follows that n times theta, rather than being uh, w times 360 degrees plus theta prime, where theta prime is non-zero, this has to be 0. And so n times theta is going to be equal to k times 360 degrees for some natural number k. I can use natural number rather than whole number because if I put 0 here, that makes n theta equal to 0, which is not going to happen because theta is strictly greater than 0 degrees by hypothesis, and n is a natural number. So this has to come out to a natural number times 360 degrees, right? For some natural number k. But just solve this equation for theta by dividing both sides by n. You get that theta is equal to k times 360 degrees over n. This is going to be strictly less than 360 degrees because theta is equal to this, but theta itself is less than 360 degrees. So if I did k times 360 degrees over n modulo 360 degrees, I get back the same thing. And that means, therefore, that theta is an inharmonic angle. And that completes the proof. Okay. Now, while we have proven in the previous theorem that an inharmonic angle will remain fixed in the n plus 1 harmonic for natural number n, we prove something even stronger in the next theorem. Namely, that for natural number n, a inharmonic angle will remain fixed in any harmonic that is equal to the value of a polynomial with constant term that is evaluated at n. As example, 72 degrees is a 5 harmonic angle. If I take a polynomial with integer coefficients like p of x equal to 4x cubed minus 3x squared plus x plus 1, and evaluate this at 5 to get 4 times 5 cubed minus 3 times 5 squared plus 5 plus 1, that comes out equal to 431. And if I do 431 times 72 degrees modulo 360 degrees, I get back the same 72 degrees. If I multiplied 431 times 144 degrees, which is another 5 harmonic angle, I get back, well, I reduce this modulo 360 degrees to 144 degrees. I'll let you check that out. Okay, here's the theorem. Let theta equal k times 360 degrees over n be a inharmonic angle where n and k are natural numbers, and k is greater than or equal to 1, but less than or equal to n minus 1. Now, that means that k is going to be less than n, and so k over n, that's a fraction less than 1, so that times 360 degrees, that's going to be less than 360 degrees, so we don't need to reduce that modulo 360 degrees. Okay, also let p equal to a sub j times n to the j power plus a sub j minus 1 times n to the j minus 1 power plus dot 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 plus a sub 1 times n to the first plus 1 be a polynomial with integer coefficients evaluated at n, and where j is a natural number. So we have natural number powers like 1, 2, 3, etc. here. And we're taking a polynomial and we're evaluating it at n. So this is not just an algebraic expression. It reduces to an actual number when we set n equal to an actual number. Okay, given that, then p times theta modulo 360 degrees is equal to theta. Theta will be a fixed point here. Okay. And let's note that P times theta, it's going to be equal to this expression times theta, which is K times 360 degrees over N. And let's see, we could rewrite this as this expression times just this part where you see the n's plus 1 times this thing. And that gives us this part here. Most of that expression times k times 360 degrees over n plus, and this was 1 times k times 360 degrees over n. Okay, now every term in this expression contains a factor of n, so you can divide each term by n, and that reduces this expression to a sub j times n to the j minus 1 power, so on, so on, so on, plus a sub 1 plus k times 360 degrees. This is going to be some natural number times k times 360, so this comes out to a natural number power of 360 degrees. And then we also have plus k times 360 degrees over n, the second term here. Hence, p times theta modulo 360 degrees. That's equal to this stuff modulo 360 degrees, which we reduce to this part, modulo 360 degrees. But since all of this is nothing more than a natural number times 360 degrees, when you divide this part by 360, you get 0 as a remainder. So when you reduce this modulo 360 degrees, you're just left with this part. K times 360 degrees over n, whole thing modulo 360 degrees. But as we argued, pointed out earlier at the top, K, since it's greater than or equal to 1, less than or equal to n minus 1, K over n is a fraction less than 1. That times 360 degrees gives us an angle less than 360 degrees. So this thing modulo 360 degrees is just K times 360 degrees over n, which in turn is our definition for theta. Okay, and that does it. We proved that theorem. All right. And it looks like that will be it for this slideshow. So I'm back. And I believe I have just one more to go in this series, so we're almost done. So I hope you enjoyed that. I hope you join me for the next recording, the next slideshow. And for now, I'll just say so long and be well.